Together with Proxima, they form the stellar ensemble nearest our world, our first neighbors beyond the long reach of sunlight. When we gaze at the night sky, we see a silent congregation of lights scattered across darkness. Yet for all their variety, the stars nearest to us form a small family, our immediate cosmic neighborhood. They are the first stepping stones beyond the sun's warmth, the threshold between the familiar solar system and the grand stellar ocean of the Milky Way. To understand these nearby suns is to glimpse both our isolation and our connection to the wider galaxy. Our voyage begins at home with the sun itself, a middle-aged yellow-white star, classified as a G-type main sequence star. It is ordinary by stellar standards, moderate in size, brightness and temperature, but extraordinary in significance. Every definition of distance, every measure of brightness, begins with this star. Its immense mass, 333,000 times that of Earth, bends space and keeps our planets bound. It fuses hydrogen into helium in its core, releasing the energy that enables not only life on Earth, but the radiance by which we see everything in the solar system. The sun's apparent omnipresence can mask the fact that it is itself moving, sailing through space at roughly 230 kilometers per second as it orbits the galactic center once every 225 million years. Even the most stable reference point is in perpetual motion. Beyond the sun lies emptiness, an enormous expanse of drifting dust and gas stretching for trillions of kilometers before another star appears. The nearest of these neighbors is Proxima Centauri, a faint red dwarf located 4.24 light-years away. To our eyes, it is invisible without a telescope, small, dim, and cool compared with our sun. Their presence reminds us that the stellar population around us includes more than steady suns. It includes failed stars, substellar embers glowing just enough to reveal their warmth to sensitive detectors. When astronomers say the stars are close, they speak in cosmic understatement. The average spacing between stars in our region of the galaxy is on the order of 5 light-years, a void large enough to swallow thousands of planetary systems whole. Despite its smallness, Proxima Centauri has drawn immense attention because it hosts a handful of exoplanets, at least 2 of which are potentially terrestrial. The most intriguing, Proxima b, orbits within the star's habitable zone, where temperatures could, in principle, allow liquid water to exist. At only 0.05 astronomical units from its star, 1/20th the distance between Earth and the Sun, it completes a full orbit every 11 days. Whether this world is livable is another question. Red dwarfs are volatile suns. They flare violently, drenching their planets in radiation. A true atmosphere may be stripped away long before life can arise. Still, the discovery reignited one of humanity's most persistent hopes, that another Earth-like planet might circle the nearest star. But what if the most intriguing neighbor isn't the brightest, or even the one with a potentially habitable planet? What if our next closest star is a cosmic speed demon hurtling through space so fast it visibly shifts its position in the sky? After Alpha Centauri comes a star known less for brightness than for movement. Barnard's star, about 5.96 light-years away in the constellation of Fucus. It, too, is a red dwarf, more massive than Proxima, but faint enough that a telescope is needed to see it. What distinguishes Barnard's star is its proper motion, its apparent movement across the sky relative to more distant stars. Over time, it drifts noticeably, covering 1/4 of a degree every century, faster than any other known star as seen from Earth. This motion arises primarily from its true velocity within our galaxy. It is hurtling through space relative to the Sun at about 140 kilometers per second. Like Epsilon Eridani, Tau Ceti demonstrates that stars resembling our own are not unique. They are scattered across the galaxy, each a potential cradle for life. Beyond them, another pair awaits. WISE 0855-0714, a frigid brown dwarf nearly as close as Lumen's duo, discovered through its faint thermal emissions. At only 7.2 light-years distance, its surface temperature is estimated around -15 degrees Celsius, not far from the cold of a winter day on Earth. If planets circle the Sun in wide, bright arcs, this object floats almost invisibly, an exile from the family of luminous stars. The diversity of our neighborhood defies the quaint imagination of 19th-century poets who pictured the heavens studded with bright pearls. In truth, most nearby objects are dark, faint, and humble. The next system outward to rival the Sun in brightness is Sirius, the celebrated dog star of Canis Major, 8.6 light-years away. Sirius A, twice the Sun's mass, shines 25 times more luminous, making it the brightest star in Earth's night sky. Its brilliance, however, conceals complexity. Orbiting it is Sirius B, a white dwarf, the dense remnant of a once mighty star that exhausted its fuel and collapsed into an Earth-sized cinder of staggering density. Each photon crossing that space carries the present of one moment and the past of another, an overlapping of times that highlights the strange simultaneity of the universe. They are the only suns within theoretical reach of exploration. Concepts such as laser-propelled sails or fusion-driven starships link their calculations to the distances of these worlds. 4 light-years to Proxima, 6 to Barnard's star, 8 to Sirius. Even at 1/10 of light speed, an audacious but not inconceivable goal, those journeys would take decades. The conversation between our reach and these distances will shape the entire future of spacefaring civilization. Within roughly 20 light-years of Earth lie about 130 known star systems hosting 200 stars of various kinds, singles, binaries, and triples. Most are red dwarfs, cool, dim suns that would be invisible were they farther away. The more luminous, sun-like stars, the ones our eyes readily find, are comparatively rare. This fact intriguingly reverses perception. The stars that seem plentiful in our sky are actually a minority. The faint ones, unseen without instruments, are the dominant population. The universe glows faintly, not because it lacks stars, but because most shine low and steady. This immediate neighborhood governs our astronomical perspective. Each of these stars represents a potential waypoint in any journey outward. Their measured distances are the baseline by which we judge greater scales, hundreds, thousands, millions of light-years. When we speak of other galaxies, we inevitably relate them back to these nearby distances. How many times farther than Sirius? How many times the Earth-Proxima gap? The distances are forbidding, yet the possibilities remain near enough to inspire. It is not empty, though. It contains the dust from ancient stars, heavy elements forged in supernova explosions, and wisps of hydrogen that will, over eons, collapse into new suns. The space separating the nearest stars is therefore both desolate and fertile, an intermission in creation, awaiting the next act. It is also a region we begin to touch, if only with machines. Voyager 1, now 24 light-hours away, has entered this realm. Voyager 2 is not far behind. Their signals, faint and delayed, mark humanity's first contact with the space between stars. Each pulse of data they send must cross one light day to reach our detectors, our first conversation with the interstellar dark. Someday, perhaps, a successor craft will cross the 4 light-years to Proxima Centauri, transforming those silent distances into geography. Understanding the nearby stars also teaches a subtler lesson. Proximity in space does not imply similarity in kind. Within just 10 light-years, we encounter blazing binaries, inert brown dwarfs, and quiet dwarfs, both red and white. Diversity is the rule of the cosmos. If we could drift outward in sequence, passing one system at a time, we'd see luminous variety, but increasing emptiness. In the next episode, we will examine the strange relationship between those distances and the flow of time itself, how the constancy of light turns every act of seeing into an act of looking backward, and how relativity transforms space, duration, and motion into one inseparable continuum of experience. Fomalhaut, 25 light-years away, is a solitary white star encircled by a dazzling debris ring, a young solar system in formation. These are still close enough that their light began moving toward us since the late 1990s or the early 2000s, light that left when the modern world was only beginning its digital age. The cosmos is timeless, yet the light we receive is ever young, a messenger arriving just a few human decades behind the present. The detailed mapping of these local stars is the purpose of orbiting observatories such as Gaia, launched by the European Space Agency in 2013. Gaia charts the positions, motions, and distances of over 1 billion stars, resolving our neighborhood and much beyond in exquisite three-dimensional precision. As of 2026, its latest catalogues measure distances with accuracy once unimaginable, an error less than a fingernail's width on the scale of the continental United States. From such fidelity, the very structure of the Milky Way emerges. The nearest stars, measured in light years, remind us of the delicate proportion between the possible and the unreachable. If you've enjoyed meeting our stellar neighbors, make sure to subscribe for more incredible journeys through the cosmos. And to continue your exploration of the universe's wonders, click on the video appearing on your screen right now.